So let's start walking through the PowerPoint presentation for this will be section 3.3, and we'll look at how to use function notation, how to interpret it. So this is 3.3. Okay, so we'll start off with a question, looking at the area of a square. I'll let you read through that, but and we know it's measured in square inches, and we're going to define S to be the side length measured in inches. So we've got this little square here. We're going to call each side S, and the area, since there's all of these are S, is going to be length times width, or S times S, which gives us a equation, a formula. That area is equal to S squared. What we do is we change things a little bit as we were looking using function notation. We give the function a name. We just call it G. Why not call it A? I don't know. S is the input variable, and so that is what's out here. But G of S is now standing for the area. So if we had a square that had 3.5 inches for each of its sides, then we want to use side length of 3, and this is and 26. I'm assuming they mean this would be, this function notation represent the areas of two different squares. I was going, is that the area? Okay, so the area of one square, the first square, of course, is going to be G of 3.5. 3.5 times 3.5 will give it to us, but again, we're just using notation to represent it, and G of 26.92 would be the second one. Okay, so we're just plugging in the length of the sides into the function notation. The nice thing about this, which we'll see later, is that when we do calculate it, 3 times 3 is 9, 35, whatever the answer is, whenever we use function notation, we have the input here, and then we have the output as the answer. So in this statement, we would have both the input and the output, which allows us to have both a X and Y coordinate, really a point that we can put on a graph. Okay, this is the same. So now how do we interpret the meaning of this one? Well, it's got a side length of 4.9 and an area of 24.01. So that's the area, the square. So there'd be like 24.01 little squares in here, right? 4.9 is the length, 4.9 is the height, 4.9 is the length of each of the sides, but to calculate area, it's 4.9 times 4.9 gives us the 24.01. Okay, and we can clear that out. So what does it mean to solve, say, the function g of s equals 81? Well, it means that we set the function equal to 81, and then we get s by itself. That's one way of saying it. We isolate the s, so we're going to take a square root of both sides and figure that one out. But we solve it in different methods, but we use algebra to get the variable by itself. And then we're finding out what would the side length be. So again, you can read through all of this, but solving for is basically we're finding what is the side length that gives an area of 81. So it's going to answer that question. So then now we're going to be asked to solve, if you remember, I think they had this one earlier, what would the side length be at 24? So we'll kind of step through this. If you solve it, right, you're going to get 24.01 equals s squared. So we take the square root of both sides, and so you'll get s is equal to 4.9 if you plug that in. you'll see that it's also could be negative 4.9, but negative 4.9 in terms of a length of a side of a square has no physical meaning. Might have some philosophical meaning, but it has no physical meaning for us. So in this case, we are only accepting positive values for the side length. So what is this? Well, remember, g of 5 is going to give us the area of a square that has a side length of 25, or sorry, a 5. Of course, the area would be 25, 5 squared. Adding 23 means we've got something else, maybe another square, but this would have to be a volume to be able to add these two together. Okay. This would be finding the area of a square that's 3.4 on each side, and then multiplying it by 4, so you're getting 4 squares, right, of this, all of the same area. So it's 23 inches more. So we got, like, maybe we're doing some carpeting. This gives us 25 square inches of volume, and then we've got some leftover carpeting that's 23 square inches, something like that. The last one is we're getting something that's 4 times as large as the area. So whatever this area is, we multiply it by 4. So we've got basically 4 of these squares. That's how much area we have. Okay. The square side length that increases at a constant rate of 3 inches per second, right? So now we're not talking about a particular value, but that as it increases, where t represents the number of seconds since the square's side length started increasing, what does 3t represent? 3 times t. Well, that's whatever the time is, times by 3. So that's 3 times the number of seconds since it started increasing. Oh, wait. Okay, now back up. Yeah, 3 times, which, okay, 3 inches per second. So that 3 represents inches, right? And then how much time? So this is the number of inches that it's, so after 2 seconds it would have increased by 6 inches, and so forth and so on. What does 3t squared represent in this situation? Well, again, 3t represents how much the side has increased. And so if you expand it, what you're going to see is it's going to be 9t squared. Yeah. So we expand it out, it's going to be 9t squared. That's going to be the area of the square when the side length has been growing for t seconds, and is equivalent to the first expression. Okay, so number of years since 2000, so 0, so this would be at the beginning, the year of 2000. We're leaving circles and area right now. But what we can see is the input quantity, the variable that we input is n, or it's the number of years since 2000. And again, so the year 2 represents 2002, and the output is going to be the price of the car. Number of years since 2000, the output quantity is the price of the car, a new Toyota Camry in those given years. So over a 20-year period, went from 17,520 to 25,925. Okay. So how do we evaluate each of these? Well, for f of 7, what we do is we come here, we find when x is 7, and then we evaluate it. It's got to be 19,920. To get the 20, we do the same thing. We just come here, when 20, there's our output answer right there. So it's just looking up in the table the values. Now, if we wanted to find f of 15, we wouldn't be able to use this table. We'd have to estimate or something, but we don't have it in this table. So they look it up. Okay, got the value. So in 2020, brand new car, Toyota Camry cost this much. sometimes we need to solve for n when we know the output value. Well, if we've got a table of values, what we do is we just come look this up. Oh, there it is right there. Now, with this particular one, since each input has only one output, it's possible that there could be more than 1 year. It could happen to 2 years, maybe like 2 years in a row the price didn't go up at all. That could be possible, but we look for when the output is 19,250, and now our answer for n is going to be right here. This is what n equals 5. And so we would say that is the year 2005. N equals 5. So we link the two values. In 5 years since 2000, we get 19,295 for the cost of the car. Again, each one of these we can then find the output. So we come to 6. It's going to be this. For 3, we look up here. There's our output. And then we take those two values and subtract them. So it looks like you can almost do that right here. In the year 2006, the price was $500 more. So this is going to be equal to 500. So you subtract those two values. And I'm sure we'll get that right there. And so it just tells us that in 2006, it cost $500 more to get the new Toyota Camry than it did in 2003. Each of these, so this one, find the function value. So we would look at year 3 since 2000. That's going to be the cost of the car. If I add $1,250, that must be some kind of, maybe some accessories I bought. Maybe I'm getting leather seating, something like that. But there's an additional charge, or dealer prep, something. But the price of the car is here, maybe a base model, and the additional is a charge for something else. Okay. So the total cost would have been $20,295. Okay. I'm not quite sure what the meaning is going to be of this, but it's obviously giving us a ratio. Again, we've got year 6, we look up its value. Year 5, we look up its value. And then what we're going to do is we're going to divide the two values. So we're getting a ratio, and which would kind of give us a percent increase between the years. So it's, you know, yeah, they did 100, or well, 100% represents that. That's the part that stayed the same. So in 2006, it was 1.2%, actually maybe rounded to 1.3% more expensive in 2006 than in 2005. 1.102 times as much. Sure, we got that. We can turn it to a percentage, though. Okay, so now we're going to talk about a turtle and a hare. The tortoise and the hare, they're having a race. We're given some information. We've got a 400-meter track. That's how they're doing. The hare gives the tortoise a 225-meter head start. When the gun is fired, the hare begins running at a constant speed of 5.5 meters. Tortoise is crawling at 2.2 meters per second. And then what we're going to do is let t represent the number of seconds since the start of the gun, right? That makes sense. And then we're going to see who won the race. So illustrate the situation with a diagram, mark off the length of the race, note the approximate position of the tortoise, all that kind of stuff. We don't know if it's well, it says a track, so I guess it could be circular. For purposes, I'm going to just list it as a track could also be straight. Why not? So there's our 400 meters. There's our little rabbit, 2 little ears. And here's our little turtle. That the distance that they start off is 225-meter head start. Here's a little turtle with a little head. And then turtle's going to be going at 2 meters. Rabbit's going to be going forward at 5 meters. So it will obviously catch up on it, but the idea is, will it be able to catch it by the end of the 400 meters, right? 400 meters is like the finish line here. So you could calculate, well, it's going to be, what, 175 meters So the turtle has to go 175 meters, while the hare has to go a total of 400 meters. Okay, but there we go. So what do they give? Let me erase all my drawings. Kind of like to talk through it. Oops. Just erase all. So you got, and yeah, they went with a straight line. You could label all the parts. 400 meters for the total race, 225 meters head start for the turtle, 2T and 5.5T. Okay, oh, I think I had 5, I didn't. So again, pay attention to rates. Okay, so that's our drawing, which is helpful as we go through and do everything. And then we could see that what the as far as the time goes, the tortoise already has 225. So if we put 2 times its at this rate, knowing the time, that'll tell us where the turtle is at any given time value afterwards. To get the distance of the rabbit, we're going to say, well, how close is it to finishing up, right? Well, we've got the rabbit has to go 400. Once it gets it down to 0, it's finished. The tortoise only has to go 175, so once it gets this down to 0, it's finished. So we've got some things that we can calculate. And then the distance between the rabbit and the turtle. Again, it starts out at 225, but the rabbit is gaining on the tortoise by 3.5 meters per second. Okay. So we've got all of that. It's fine. So define a function g to represent the tortoise's distance from the finish line in terms of the number of seconds t since the event started. We did that. At least that was done, right? So we're going to call it g of t based on the time. And it just needs to be a distance from the finish line. Starts out at 175 and then getting closer by 2 meters per second. Okay, find h represents the hare's distance. Again, we did that on the last one, but it will be h of t. And again, it starts off at 400 meters and then getting closer by 5.5 meters per second t. Okay, and they give us that. So let me erase mine so you can see those values. Evaluate g of 40. So remember, that's going to be the tortoise's location, how far it is from the finish line 40 seconds after the start. So if you do the calculation, 175 minus 2 times 40, you get 95. And solve for g of t equals 80 for t. So that's, again, what we're solving for is how many seconds before the tortoise is 80 from the finish line. Notice it probably should be a little bit more than 40 seconds because at 40 seconds he was 95. So we'll see how that works. What we do is we, again, we've explained it. If you solve it, you get 47.5, which makes sense. It should be more than that. And again, the way we went about what you would have done to get this is you would have said 80 equals to 175 minus 2t. So solve this for t. I would subtract 175 on both sides and then divide both sides by -2. That's how you get this. And then it's just, yeah, tortoise is 80 meters from the finish line, 47.5 seconds. Now we go to the hare, solve for h of t. Well, that's at time, when is it 0? So what does this mean? Remember, h of t is the distance to the finish line. So this is when does the tortoise cross the finish line. That's probably an important number to have. So again, we had this equation 400 minus 5.5 t. We want to find when is that going to be 0. When we solve that, what we're going to find is how long it took to finish. If you do the math, you get about 72 seconds, almost 73, and that's when the distance to the finish line is 0 meters. Okay, so that's how long it took the rabbit to finish. We could construct a graph of both of these, and that's being done for us. So what we see is the tortoise is the H, so this is their, you can see at any given time they're getting closer and closer together. And what you see is that the rabbit actually crossed the finish line sooner than the tortoise. So this is about right here at about, 65 seconds. That's about when they cross. The rabbit passes the tortoise at that point. So evaluate h of 20 minus g of 20. So that was shown on the graph, and that'll show the distance. Again, since h of 20 is the distance of the rabbit, of the hare to the finish line, and g of 20 would be the distance of the tortoise to the finish line after 20 seconds. It's going to give us the distance between the two. So how much of a lead does the rabbit still have? We could calculate that from the graph going back there. We could use the formulas, but we see that the lead that the tortoise has is shrunk down to 155 meters from the initial lead that it had of 225. So rabbit's catching up. And that's 20 seconds after the lead is gone, shrunk to only 155 meters. So now let's look how we can actually define this as a new function, right? What's f of t? Well, it's the function h of t minus g of t. So to do that, what is h of t? We go back to our start. It's the distance of the hare to the finish line, right? So that was 400 minus 5.5 t. We're going to subtract, and I put a parentheses around this, g of t, which was the tortoise's distance to the finish line. That was 225, where it started, minus 2t. Notice we have to take this negative and distribute it. So this negative 2t becomes a positive 2t. This positive 225 becomes negative. So you end up with f of t further than I need to, but that's okay. 400 minus 225, there's the 175. Negative 5.5 plus 2 is going to be negative 3.5 t. And again, what that's going to give us at any given time is the what the distance between the two. Did I do that right? This goes here. 225. 400 minus 225 is, oh wait, no, 175. It's going to add, okay. The thing is, this should give us, so what is this? So, this is the distance, distance to the finish line. Distance to the finish line. You subtract the two, it should give you the distance between the two at any given time. Oh, that's where I'm wrong. This 225 is wrong. I had to switch those. Remember the tortoise. Because what I was doing is I was plugging in 0 for t, and I know that at time 0 at the start of the race, the tortoise is 225 ahead. So it wasn't making sense to me, because the formula for the tortoise, the finish line is 175 minus 2t. So then 400 minus 175, that's the 225. Now this makes sense. At time 0, there is 225 meters between the two. As time goes on, the distance between the two goes down. Okay. So let's take a look. And that's why I kind of go through these, talk you through them, rather than I could just do this and it's got all the values. But I want you to see where everything comes from. Okay. So that's going to give us the distance in meters between the two. So how much lead does the tortoise have? You see it's shrinking and shrinking. That's f of t. It really is just the difference between the inputs and the outputs, or the outputs of h and g, which are their distance to the finish line. So remember, when we start off, there's always, it depends on our perspective, what are we trying to measure. So h and g measure the distance to the finish line. F of t is going to measure the distance between the participants. Okay, so we see f of t, it's not so important here, but what we see is that the distance between the two becomes 0 here. Now, if it were to keep going, then that would, what we're reading is this negative value means that now the tortoise is that far behind, right? So we could have negative values here, but we also see that that corresponds to the place where they cross, where this is where they're equal now. Their distance between each other is 0. Okay, let's keep moving. So what is the slope of the graph of f? The slope is, that is the rate that the hair is closing in on the tortoise. And it's kind of it's a combination of the two slopes. So notice the hair is going much faster, it's steeper. The tortoise is going slower, it's not as steep. And f is kind of in between those two. It's steeper than the speed of the tortoise, but not as steep as the speed of the hare. Because as the hare moves at 5.5, the tortoise is still moving ahead, so it's only catching by 3.5 per second. Okay, so it's negative 3.5. That's how the distance between the two is changing. Okay, so where are they equal? Again, we saw that on the graph. It was about 60 seconds, but we'll just walk through this. We set the two equations equal to each other, and yeah, I said about 65 from the graph, but what you would have to solve for is, what is g of t? Well, that's the tortoise. That was 175 minus 2t. You set that equal to 400 minus 5.5t. When you solve that for t, you see that that happens at 64.28 seconds. That's where they are going to be passing each other. They're going to be at the same location. There is no distance between them. Okay, so who run the race? Well, we saw from the graph, the hare did, right? He finished first. When he got the distance between the hare and the finish line was 0 before the tortoise was. Okay, and we could also see from what we did before that it only took 72 seconds for the hare to get to the finish line, while it took 87.5 seconds after the gun for the tortoise to get to the finish line. And the finish line is the same place for both of them. So, you know, you can even see, oh, it was what, 15, almost 15 seconds between the two finishing. So we also can use this for another situation. So what we have here is we're filling a wading pool, and we've got the volume of water in the pool in gallons going in and the elapsed time. So as we have time going in, we can measure after 7 seconds there are 14 gallons of water in the pool. So we could come up with a function. It looks like every minute we get 2 more gallons. Every minute, 2 more gallons. And we're starting at 0, right? So our y-intercept would be 0. So we could say, what do they want? they want, do they give us a function? But anyway, we're getting, yeah, so our y equals 2 times t. So every minute we get 2 more gallons. Okay, 2t, g of t. I thought they wanted, yeah, here it is. They want a g. So g of t equals 2t. That's good. So what is g of 4 minus g of 1? Well, that's the additional water that has gone in from 1 minute to 4 minutes, right? So we got 2 here, we get to 4. We have a total of 8, but we already had 2, so there's an additional 6 that went in there. We can see that from the graph, or we could go ahead and calculate it with the formulas. But when we have a graph, we can actually look up various values. Well, I don't know why I'm going with 2, but anyway, here's 2, and I could go to 6 and say, okay, that's going to be its value, and then we could subtract the 2. But with the graph, it doesn't fit. We're not doing calculation math, but we're doing math by reading the values off of the graph itself, much like we could do with a table. So they show that there, 1 and 4. Okay. So what could g of 4 plus 100 represent in this context? Well, that would be the number of gallons after 4 minutes, plus some 100 gallons sitting around someplace else, right? So it's 100 gallons more than what was put in the pool after 4 minutes. So 4 minutes there was 8. So I don't know. Maybe we're the hose that it's coming from. Maybe that's the tank it's coming from. I don't know. But there's 100 gallons more there. So how many gallons remain in Pac's gas tank after he has driven for 84 miles? So here we go. We got all this to read, but the important part is he had 8 gallons of gas in the car's gas tank, and his mileage was 32 miles per gallon. Assume that he maintains his gas mileage by leaving cruise control on. Pat needs to keep track of how much gas is left in his tank so he doesn't run out, right? Because his gas gauge is broken. So we know, so what, how many gallons remain in gas tanks after this. So what we have is we have 8 gallons, and what we're going to do is we're going to subtract a gallon every time we go 32 miles, right? So how do we make sure we get that done? Well, we need a rate. So 1 gallon for every 32 miles. It's one way to think of it. And this is a rate, and that's how we're going to use it. And so this will be times the number of miles. So when we go 32 miles, 32 divided by 32 will cancel out here. We'll see that we'll have 8 minus 1. If we go 64, 32 divided into 64, that's 2 gallons that we've used, so we'd be down to 6. Seems to work. Seems to work. Okay, so 84 divided by 32, and yeah, that's where the m could be up there, is 2.625 gallons. So you subtract them, that's what we have left. Okay, same thing after 150 miles. Well, you have to take the 150 miles divided by the 32, and then whatever that is, that's how much has been used. You have to subtract that from the 8 gallons, because again, what you're interested in is not necessarily so much how much you've used, but how much you have left, so that you don't run out. So you used up 4.6 gallons. You still have 3.3 remaining. So you can say, okay, now might be you want to think, how far can I go with these 3.3 gallons? What you'll see is we'll end up multiplying by 32 instead of dividing by 32. So again, building us up to a variable. If we have X miles, it's X over 32. So that's really what we were doing. One gallon for every 32 miles, X, and we get this function made up. Okay. And so we can do these calculations. If X is the number of miles, we just plug in the number of miles we've used, and that's really what we've been doing as we build it up. So what is the domain of f? Well, the domain of, we can plug in any values we want until, I guess, the gas tank is empty. So what we'd have to do is we'd have to see x really could be anything mathematically, but we'd want to solve for what x value would give us a 0, right? So you could subtract this. So if you take 8 times 32, that's what's going to tell you. So x can be anything from, and again, x is number of miles, so it could be 0 miles up to 8 times 32. See, 8 times 2 is 16. 8 times 3 is 24. So that'll be 256. So that's the number of miles we can drive. The range is just, you plug in this, obviously the output will go from, really from 8, because that's what we're starting with, down to 0. You can't get negative gallons in the tank, but 0 to 8. The domain is 0 to 256, since that's when all of 8 gallons will be used. And then the range is 0 to 8 gallons, because gallons is the output, how many gallons are left. Now again, it starts at 8 and goes down to 0, but we always go left to right with the smallest to the largest. Okay, what does f of 100 represent? Again, that's how many gallons are left. Remember, that's the f is representing the output. This is the number of gallons left after driving 100 miles. Construct a graph. Let's let them do that for us, right? So we could, at 0, he's got 8 gallons. We could do a few calculations. At 32, somewhere here, he'd be at 7. And we knew that at 254, we'd be at 0. So actually, all we need is 2 points, and we know since the rate of change is constant, it's going to be linear. What does it convey about the number of miles Pat has driven since the gas gauge broke, x, and the number of gallons of gas left in? Well, it's telling us the rate of gas that is getting used up per mile, right? 32, you'll go 32 miles on 1 gallon for 32 miles. So yeah, it goes from, so the range from 0 to 256 miles, you'll run out of gas after that. And that is gas in the tank goes from 8 to 0. And hopefully don't try to run it all the way down unless you have a reserve tank somewhere. So what's the value of f of 0? Well, that f of 0, that means he's driven, that's when the gas gauge broke. That would mean that there are 8 gallons left in the tank, right? So since he's driven 0 miles, that's what happened. F of x equals 0, well, this is going to give us how many miles he's driven when the tank is empty. And again, we've already calculated this to be 256 miles, I think it is. So yeah, after 256 miles, there's nothing left in the tank. So f of x itself, what's the maximum minimum? We calculated that as the range. The maximum, we start with 8 gallons, and the minimum, we end up with 0 gallons. The maximum value of the f of x can be also the maximum value of the function. How do these values compare to f's range? They are the range. Okay, 0 to 8. Okay, so 0 is the smallest, 8 is the largest. That's the range. Those are the outputs. The horizontal intercept, which is a 0 or the root, that's where it crosses. And again, that's when y becomes 0. So that was 256, 0. So after 256 miles, y becomes 0. That's the x-intercept. After 256 miles. We saw that from the graph. And we can also see that that means that all 8 gallons would have been used. And that is the last slide we have for this. So this is how you go about using it. And I thank you for sticking through with this. Keep on working forward, and making good use of these videos. Again, you can watch them at faster speeds and so forth, and then work on the homework.